Hello and welcome. This video tutorial will help with uniform circular motion problems. When you look at these problems, there are four questions we're going to be looking at. The first question, number one, is called O snap. O snap is a question in which case a string will snap at a certain point, and we have to, let me see, let me call that up. We have to be able to determine the number of RPMs, that's revolutions per minute, to make a string hold an object in circular motion snap. In addition to giving the revolutions per minute, the RPMs, you must also determine the speed of the ball in meters per second at the moment when the string will snap. The second question is called force normal on a spinning space station. So for this question, you're going to be essentially determining the number of revolutions per hour you must give a spinning space station so that you create a force normal where the occupants would match the force for a given gravitational field. So for example, if you're given a gravitational field that the astronauts are supposed to experience, let's say on Earth, 9.8 meters per second squared or 9.8 newtons per kilogram, then your goal is to create that by spinning the space station at the right revolutions per hour. Okay. You're creating what's called artificial gravity, and the normal force of the spinning of the station is pushing against the astronaut's feet, creating what's called artificial gravity. But you're going to be given a gravitational field that you have to match this data for. So that's question number two. Question number three is called car on a turn. In this program, you're going to basically make your car successfully be able to round a turn without slipping. You'll need to calculate the force of friction and the maximum speed it can go around the turn. Okay. And then finally, question number four, you're going to have what's called a vertical circle. So in this challenge, you're going to whirl a bucket of ice water in a vertical circle without having the water spill out onto your head or the string breaking when the bucket is at the lowest point of its loop. It will randomly generate a mass of water and a rope length. Your job is to find the minimum speed at the top and the maximum speed at the bottom that the bucket can have without violating the conditions that we stated earlier. So there we go. Let's go ahead and get started. Question number one. Oh, snap. Okay, go ahead and make sure that you are putting your name in so you can begin. Now, a couple things to note about this question here. Okay, so we have to measure the radius of the circle. Okay, and you can see that it measures from the origin point. So we have to measure the radius, and you can see where the ball is right now. We're going to use the breaking strength of the rope to determine the speed of the ball when the string breaks. And then finally, we'll figure out the number of RPM. Okay, so you can see at the very top of the screen, we're given the breaking tension, the maximum tension. In my case, it's 7.91 newtons, and the mass of the ball, 391 grams. Write down your information. I'll write down mine. So T max, I'm going to call breaking tension T max, is 7.91. Write down yours. And your mass is going to be in grams, so you have to convert it. Right? 390 grams would be 0.390 kilograms. Okay. I would even go so far as put the ball where it is so you can measure the radius. For me, it's at, let's see, 0.5, 1.6. Okay, so let's see, 0, so 0.5, 1.6. The ball is exactly right here. So that means the radius of the turn will be at 1.6 at every point, right? That would be the circle that gets created, okay? So there's our radius right there, 1.6. Now it should be in meters. Yeah, the graph is in meters, so for me it's 1.6 meters. Now, this is meant to be a horizontal circle, okay? So the only force that's causing, if you look at the forces that are acting in here, tension, if I draw the forces, tension is acting toward the middle of the circle at every point along this pathway. In other words, tension is our centripetal force or our causing force. Okay, so we're going to go ahead and use Newton's second law. Newton's second law, uh, I guess I can call it something different. I can call it UCM, Newton's second law. Okay, so we're talking about centripetal acceleration, not regular acceleration. So the way this is different is it's causing force minus opposing force equals ma. Remembering that a centripetal acceleration is v squared divided by r. Well, the causing force actually points into a circle. The opposing force actually points out of a circle. And the acceleration is v squared divided by r. So I would write this as mv squared divided by r. Well, since there is no force pointing out of the circle and the force pointing in is tension, T max equals mv squared divided by r. So that's what we're going to be using, and we're going to use that to calculate the speed, because you can calculate the speed from there. So let's go ahead and do that. T max equals mv squared divided by r. Now, to solve for v, the speed, you have to multiply by r, divide by mass. Okay, and you can see if I do that, I get r times t max over the mass equals v squared. And so the last step you can see I need to do is I need to square root, and that will get v by itself. So v is going to be the radius, which for me is 1.6 meters, times your braking strength. For me, that's 7.91 newtons, all divided by the mass, which for me is 0.390. Okay, take a moment to figure out yours. I'll go ahead and figure out mine. Okay, I'm getting a speed of about 5.7 meters per second. So now it goes on to show, it says, show the calculation for the RPM of the ball when the rope breaks. Well, so the thing that you guys got to understand is that if we're talking about speed, we're talking about if this is the rope, okay, and this is the ball, and this angle is initially at 0. As the ball rotates, it's sweeping at an angle of 360 degrees, or 2 pi radians. 2 pi radians equals 360 degrees. So radians is just another way of measuring an angle measurement, okay? And so when we're measuring how fast something is rotating, that is going to be we're essentially solving for omega, that little variable that kind of looks like a small w. That's the Greek letter omega. And omega stands for the angular velocity. That means how fast is something rotating or spinning? If it's spinning on its axis, how fast is it spinning? So how fast is something revolving or rotating? Okay. And it's measured in radians per second, not meters per second, because radians is an angle measurement. Okay. So what we got to do is we then have to convert from radians per second to revolutions per minute using that conversion factor. 1 radian per second equals 9.55 revolutions per minute. Well, the way we do this is we use another relationship between linear and angular speeds. And that is the linear or tangential speed at the end is equal to the radius times the angular velocity. So we can solve for omega by dividing by the radius, like this. So the angular speed is going to be the linear speed divided by the radius. We'll go 5.7 meters per second over 1.6 meters. And that's about 3.56 radians per second. Now I'm going to treat radians per second as 1 unit so that I can convert it to revolutions per minute with that one conversion. So to do that, I'm going to put radians per second down here, and I'm going to put revolutions per minute up here. And 1 radian per second is 9.55 revolutions per minute. That tells you you're going to multiply those two things right there. So go ahead and do that and figure out your omega, but in revolutions per minute. Yeah, for me, I'm getting pretty much exactly 34. 34 revolutions per minute for that ball. Okay, go ahead and figure out your values. I'll go ahead and input mine. Okay, it's immediately going to start to rotate, and it's going to see how long it takes to get all the way around once. Okay, and there we go. So the predicted revolutions per minute. So that was the number of revolutions that it undergoes. It would undergo 34 revolutions in 1 clock minute, and the actual predicted speed, the linear tangential speed, would be about 5.7 meters per second. Again, hopefully you were able to get this right as well. All right, if so, we're going to go on to force normal on a space station. Okay, now in force normal on a space station, your goal is to determine the new number of revolutions per hour that you have to give a spinning station to create a normal force for the occupant that matches the given gravitational field. So in this box, in this area over here, we're going to jot down some of the data we're given for this problem. And then honestly, all we need to do, guys, is we need to calculate the centripetal acceleration. And the centripetal acceleration will match the gravitational field. Okay, and then once we have that, this is going to match the gravitational field. We're going to solve for speed. Okay, and then once we have the speed, we'll go ahead and solve for omega. Remember, omega is in radians per second. So we have to change radians to revolutions and seconds to hours. And you've got the two conversions right here. 1 revolution is 2 pi radians of angle measurement, and 1 hour is 3,600 seconds. Okay, so that's the information that we've got. So actually in part 1 right here, that's where we're going to record everything. Okay. First, record the force normal. It's going to be equal to the weight, the mass of the person, record that, record the radius of the space station, and the gravitational field strength. So go ahead and get all that. Press begin. So on my question, it says, well, the space station that you are on, that you are controlling, has a radius of 884 meters. Go ahead and write your information. To create a normal force for a 59.4 kilogram person, 59.4 kilogram person, and we'll figure out the normal force on that in a second, of the ship that will match a normal force they would experience on a planet with a gravitational field strength of 4.8 newtons per kilogram. So G, which is the same as your centripetal acceleration, is 4.8 newtons per kilogram. Well, my value is 4.8 newtons per kilogram. Okay, now normal force is going to be balancing the weight. So 59.4 times, don't go 9.8, use the G that you have here. In this case, 4.8. Okay, figure out your normal force. I'll figure out mine. Okay, so I'm looking at a normal force of about 285.12 newtons. So that's the first thing we have to do, is we just have to get our information down. And once we have that, we'll just go ahead and solve for omega. So getting the number of revolutions per hour is omega. but then omega in radians per second, and then convert to revolutions per hour. Okay, that's the goal. That's what we're going to try to accomplish. So this is actually a very, very easy question. Now, there's obviously a lot of room for error and making mistakes, just like there is with any question. So try to be careful. I know I'm going to try to be careful, but mistakes do happen. Okay, we'll obviously try to minimize them. So I'm going to take uh, my centripetal acceleration equation, because my centripetal acceleration is my gravitational field strength. It's equal to v squared divided by r, and I want to solve that equation for v. So in order to do that, I'm going to have to multiply by r and then square root. Okay, and if I do that, v is going to be equal to r times my centripetal acceleration. So my radius, 884 meters, times my centripetal acceleration, 4.8 newtons per kilogram. All right, I'm going to figure out my linear speed. Figure out yours, I'll figure out mine. Okay, don't forget to square root. I'm looking at about 65.1 meters per second of linear speed. That's not the answer, okay, because we got to basically find omega in radians per second and then convert that to revolutions per hour. So if you recall, V equals R omega. So omega equals V divided by R. So I'm going to go 65.1 meters per second, divide that by 884 meters. Which gives me a rate of rotation of about 0.077369 radians per second. Okay. Now, here's what we're going to do to finish this problem. I'm going to convert radians to revolutions. So there are 2 pi radians in 1 revolution. That cancels. Then there are 3,600 seconds cancels, in 1 hour. Now you can see my units are in revolutions per hour, and I've got the correct unit for it. And the math should take care of itself. You can see I'm going to be multiplying this times this times this, and then just divide it by 2 pi. And when you divide by 2 pi, honestly, you're the closest approximation. If pi approximates to 3.14, 3 decimal points, or 3 digits, excuse me, then 2 pi just approximates to 6.28. So it's just, go with an easy approximation. It's fine. You don't have to be perfect with it. Okay, so 0.07. So then we're going to go times 3,600 divided by open parentheses 2 pi. See, I can't even find my pi button. Where's my pi button? Okay, pi. Good, got it. And I'm looking at about 42.2 revolutions per hour would be needed in order for that astronaut to feel a gravitational strength of 4.8 newtons per kilogram. Okay, so as soon as you're ready, then what you're going to do, and when you're ready, you're going to click on the end button. You see the end button right there? You're going to click on that, and it's immediately going to prompt you to put your name in and the revolutions per hour you calculated. Okay, and then after you type in your answer, click on the space station. So you'll click on the space station right here, and it says you will need to reach 285 newtons when you reach 4.42. So let's see how I did. Okay. Okay. So my predicted rotation was 42.2. My space station had a radius of 884. Passenger, again, had a mass of 59 kilogram. Said to create a force normal of 285.12 newtons. This would need to be the same as a G field of 4.8 newtons. This would require a circular acceleration of 4.8 meters per second squared. This would require a linear speed of 65.1 meters per second. That's what we found. This would create a linear distance of 234,503 meters in 1 hour. The circumference of the ship is 5,554 meters. This corresponds to 42.2 rotations or revolutions per hour. So in other words, my predictions were right on. Okay, so hopefully you were able to get this done and correct yourself. If not, pause the video, try it again. Okay, and mistakes do happen. They happen to me. You've seen it happen already. But let's try and practice until we can't get it wrong. Okay, that's our philosophy. Practice until we can't get it wrong. If you did get it right, let's move on to the next one. The next one is called car on a turn. Car on a turn. So below is a picture of a turn in the road as viewed from above. Draw your car at the halfway point on the turn. So in other words, like right here. Okay. And then show an arrow for the direction of the force friction at that moment. Also, fill in all the important information about your system in the box next to the picture. Okay, and we're going to show our calculation for the force gravity of the car, force normal from the road, and all that. Okay, and what actually would be helpful is to draw a side view picture too. So this is looking, so if our car is right here, so if I draw my car right here, my car is headed that way, okay? Then if I looked at it from behind, here's my car from behind. Okay, right there's the license plate. There's the bumper. Okay, and there's the two wheels. Okay, you can picture that my car is going into the page. Okay, you're looking at my car from behind. Well, I would have the weight of the car going down. I would have the normal force balancing that going up, and I would have the friction from the tires pointing in to the center of the circle. That's exactly what I'm drawing here is the friction. You do see that this right here is just part of the curvature of a circle. So friction is my causing force, my causing force of curvature or my centripetal force. Okay, so that's what I need to set up this problem. Now, let's take some time to actually write down the information in our given problem so we can get this done correctly. Okay, so for me, mass of 605 kilograms. Okay, radius G and mu. Radius G and mu. Okay, radius G and mu. Radius 82, 6.3. 82 meters, 6.3 newtons per kilogram. And mu on this road is 0.82. 0.82. That means good rubber on the road. Okay. All right. So it says use Newton's second law to get the maximum safe acceleration going around the turn. Well, if it's telling you to use Newton's second law, use Newton's second law for centripetal forces, right? Because you're accelerating in a circle. Okay, this is circular acceleration. This is not, it's centripetal acceleration, not linear acceleration. Okay, so we'll go causing force, that would be forces pointing in. That's Newton's second law. Minus opposing forces, that would be forces pointing out, equal mv squared divided by r. Well, what's going on here? Couple things to note. This value here, mv squared divided by r, that is the centripetal acceleration. So if I were to rewrite this, and by the way, if you look at the picture, there are forces pointing into the circle, but there are no forces pointing out of the circle, okay? So there are no opposing forces in this problem, but friction is the causing force. So friction, that's my force pointing in, okay, is equal to m, and instead of writing v squared over r, I'm going to write ac, because I'm solving for acceleration. Okay, now the next thing I'm going to do is I'm going to substitute for friction. Okay, friction is mu times normal force, and that's equal to mac. Well, now I'm going to substitute for normal force. Okay, so if I substitute for friction first, now I'm going to substitute for normal force. Remember, from above, normal force balances the weight. So that means this should be mu mg equals MAC. Okay, you can see that this is mass independent, so even though we were given the mass, it doesn't matter. And so AC is equal to mu times G. Okay, figure out your acceleration. All right, I'm looking at about 5.17 meters per second squared. Okay, it says now show the calculation for finding the maximum safe speed to go around. Well, now you can take this and we can now use this right here to solve for Vmax. To do that, you have to multiply by R and then square root. So V equals the square root of R times my centripetal acceleration. The radius was 82 in my case, times my acceleration, 5.17. Don't forget to square root that. I'm looking at about 20.6 meters per second. Okay, so let's see how we did. Acceleration and max speed. Okay, oh, we got to find force friction and max speed. Okay, we can do that. Force friction, go back. So force friction is going to be, you can see it's going to be mass times AC. So to find force friction, all I have to do is just go mass times my centripetal acceleration. Now it's mass is involved, which is 60, can't even read my own writing. It's 605. There we go. So it's going to be 605 times 5.17. All right, I'm looking at about 3,128 newtons and 20.6. All right, there we go. Okay, hopefully you were able to get question 3 correct as well. Okay, if so, on to question number 4, fourth and final question. This one is our ice bucket challenge. So in a picture, we have an ice bucket in a random location. Fill in the important information about the details, the mass of the bucket, radius of the circle, strength of the rope, all that. Okay, so mass of the bucket and water, 0.58. Radius of circle. Strength of the rope would be tension. That's 102 newtons in my case. Okay, and what we're looking for, we have to find the maximum speed at the bottom so that the rope doesn't break, and the minimum speed at the top so that the water stays in the bucket. Okay, so that's what's happening right there. All right, so let's draw the forces on the bucket in the 2 locations. Start with the top. So at the top, you have the mass and the, excuse me, the weight equals mg of the water and the bucket, and you have the downward tension in here. So you have 2 forces that point to the center of the circle. You have 2 causing forces. You have no opposing force in that instance. Now, because that's right here, you can see it's at the top of the circle. There's the circle right there. Okay, now if you draw the circle, again, you can see that the okay, we go over to the other one. Here's the circular path right here. And at the bottom of the circle, you've got the weight equals mg. It's not just pointing down. You'll notice it's pointing out of the circle. That makes this an opposing force. Tension is not just pointing up, it's pointing into the circle. That makes this a causing force. Okay. All right. So now, step 3. Let's find the minimum speed first. I'm going to divide this page in two. You go ahead and do the same. So V min at the top, V min at the top. So that's what we're finding up here. And then over here, we're going to find V max at the bottom. Okay. Now here's the deal. At the very top of the pathway, it's going so slow that it's just barely fast enough to keep the water in the bucket. And the only thing keeping the water going in a circle would be the weight of the bucket and the water itself. Okay, in other words, for the minimum speed case, the tension goes to 0. Okay, so if I were to look at that, my Newton's second law equation, forces in minus forces out, and there aren't any, equal mv squared divided by r. Now, normally there's two forces in. There's tension and weight, mg, equal mv squared over r. But we just saw in the case of minimum speed, if this is v min, then tension goes to 0, and it's just mg that's causing it to happen. Notice that the masses will divide out on either side, and this equation very much simplifies to G equals V min squared divided by R. So solving for V min, you can see we have to multiply by R, okay, and then square root. So V min would be the square root of GR. Okay, got to find whether or not this is on Earth. I didn't pay attention to that. It doesn't say if it's somewhere on another planet with a different gravitational field, so we're going to use 9.8. Okay, and the radius of the bucket, 1.73. Okay, about 4.12. About 4.12 meters per second is the slowest speed it can have for the water to still remain in the bucket. Now, at the max speed, you're going to do the same thing, okay? Newton's second law, but at the bottom, we have forces going into the circle minus forces going out of the circle. Those are opposing forces, equal mv squared divided by r. Well, going into the circle would be tension. Going out of the circle would be the weight, mg. And that is equal to mv squared divided by r. This time you're looking for v max. So in order to solve for speed, you're going to need to multiply by r, all of that. You'll need to divide by mass, all of that. And then finally, you'll need to square root. And so V max is equal to R, the radius, 1.73, times the tension, which I have 102 for mine, minus mg. So the mass is 0.58. 0.58 times 9.8. Okay, and then all of that is divided by the mass of 0.58. Okay, go ahead and calculate your Vmax. I'll go ahead and calculate mine. I'm getting about 16.9 meters per second for that one. So there's a big speed difference. You can see maximum speed at the bottom and minimum speed barely getting over the top. Go ahead and put your answers and solutions in, see how you did. I'll see how I did. Let me just double check. 4.12. All right, and there we go. Okay, so this concludes our uniform circular motion problems. Hopefully you were able to be successful in your problem solving. If you had trouble with it, try again first. Okay, if you're still having trouble, please come and see me and we will work that out for you. Okay, all right, so until next time, we'll see you.